Hi, my name is Yi Chen, and I'm a Senior CFD Development Manager at Altair Engineering. I obtained my PhD degree in Aerospace Engineering from Rensselaer Polytechnic Institute. Since graduation, I have been working at Altair on CFD development. I focus on various topics including finite element method, fluid structure interaction, and high-performance computing.
Thank you for attending this talk. I'll first give you a brief introduction of Altair and AcuSolve. Then we will focus on recent development of AcuSolve on AMD Radeon GPUs. And I will present you the speed-up results of several benchmark cases. Altair is a public company that was founded in 1985. 2019 revenue of 459 million. The company is more than 3,000 engineers, scientists, and creative thinkers located in 86 offices in 25 countries across the globe. Support Altair's more than 11,000 global customers with more than 150 Altair and partner software products. The Altair portfolio of solutions have grown significantly over the life of the company. Originally founded on modeling and visualization tools, the company has expanded to provide world-class physics simulation and high-performance computing capabilities. These solutions are enhanced through the addition of IoT and data analytics. Altair's broad partner alliance companies extend even further the benefits provided to our customers. Altair's large customer base includes business leaders across a wide variety of industries. These industries range from automotive and aerospace to energy and industrial goods to education and financial services. Regarding computational fluid dynamics solutions, Altair offers several powerful products addressing a wide range of applications. This talk is about AcuSolve. So AcuSolve is a general-purpose CFD solver with a history of 30 years. It's based on stabilized finite element method with Glerkin least square formulation. We support ALE and all the mainstream RAS models, as well as a wide range of physics, multi-phase flow, FSI, thermal, and so on. Key reasons to AcuSolve's proven success in large-scale industrial applications are its accuracy, efficiency, and robustness. AcuSolve can handle extremely distorted mesh. The convergence remains equally excellent, and the results remains sufficiently accurate. Of application areas, we focus on fluid structure interaction, thermal management, multi-phase flow, internal and external aerodynamics. In this talk, I will first introduce computational characteristics of AcuSolve's two components and how they scale with CPUs and where we should apply GPU acceleration. Then I will show you the speed up we have gained on the AMD Radeon Pro 7 GPU. And at the end, we will discuss the source code porting procedure. Now let's examine AcuSolve's components. Almost every finite element code needs to repeatedly solve large-scale sparse linear systems, which come from Newton's iterations for solving a nonlinear algebraic equation. Right here, when I say large scale, we are talking about tens or hundreds of millions of degrees of freedom. So crudely speaking, AcuSolve consists of three parts: input-output, which is not our focus today; finite element formation, basically forming this AX equals to B system, and the linear solver, right, solving AX equals to B system. Those two parts, finite element formation and the linear solver, have quite different computational characteristics. The one is CPU bound, and the other is memory bound. Thus, the scalability of those two are quite different. In steady-state simulations, the linear solver part is the most time-consuming part, okay, which can take up 60% to 80% of the total runtime, usually above 70%. So it's a memory bound. So it is an obvious choice for us to port the linear solver to GPUs first. Right? Our linear solvers, they are all iterative solvers, which are customized based on classical CG and GL solver. For memory bound programs, the speed up of the runtime is limited by the memory bandwidth of the machine. Adding more CPU cores won't make it run faster. I have used the well-known stream program to test the memory speed on the CPU workstation. Now here in this chart, the threads were bound on cores as close as possible. So not all the memory resources, like the L3 cache, can be utilized efficiently and sufficiently. So when we increase the number of threads, more memory resources can be utilized, right? So the memory intensive operations of like copy and the triad can speed up to a certain level. But the memory effect is more pronounced if we switch the thread binding policy to the so-called thread, right? Basically spreading the threads across the whole system so that they don't have to compete for adjacent resource. So starting from 8 threads, the speed of the copy and the triad won't change much. So as we can see, using 16 threads instead of 32 can give you a better memory speed. So one advantage of GPUs over CPUs is the larger memory bandwidth, right? Which is good choice for memory bound programs such as large-scale sparse linear solvers. This chart clearly shows the benefit of GPUs. We can see those basic linear algebra operations used in iterative solvers such as sparse matrix vector product, dense matrix vector product for tall and skinny matrices can gain impressive speed up. The GPU used here is AMD Radeon Pro 7. Here as an example, let's examine one linear solver used in AcuSolve, the GCRODR. It is used for the scalar equations such as thermal and turbulence models, and as well as compressible flow. The algorithm is based on this paper by Parks et al. Here we can see that the GMRS procedure is only one line in this algorithm. We don't need to get into details here. Just by looking at some keywords in the algorithm, such as Gram-Schmidt, projection, QR decomposition, we know that this solver will benefit considerably from GPUs. And the AMD GPU HIP ROCm APIs, such as ROCsparse, ROCplus, ROCsolver, will be used extensively. Now let's talk about linear solvers. What are they and how to port them to GPUs? First, the linear solvers are iterative linear solvers based on the popular CG and GMRS methods, but they are highly customized for CFD problems, especially the incompressible flow problems. The solvers have sound and rich mathematical foundations. Now, one of the difficulties of porting the solvers to GPUs comes from the fact that, programming-wise, our linear solvers are entangled with many other features for the purpose of efficiency. Now, for example, our Dirichlet boundary condition, especially the complicated multi-point boundary conditions, are implemented using the subspace projection method, which is robust and accurate, but it is completely embedded in our iterative linear solvers procedure. The other thing is the communication caused by the mesh partitioning, which it is much more expensive to communicate on the matrix level than the vector level. So we exploit the procedure of the iterative linear solver to do the vector level communication for the purpose of efficiency. And also, our sliding mesh feature is embedded with the linear solver. Now the question is, can we simply copy the CPU code to GPU line by line? In fact, this was the first thing I did for a quick and dirty trial. The answer is no. I implemented a simple CG solver with this naive way. The code runs, but the efficiency is a disaster. The reason is that the data structure of legacy CPU code is very well organized, highly layered, and hierarchical. The data in memory is scattered and segmented. We all know this cannot be the data structure to feed GPUs for data parallelization, right? So we actually had to start from scratch to design and implement data structures that are suitable for GPUs. Now, eventually, the effort paid off. What we have done is kind of like taking out all the underneath Matryoshka dolls and line up them for the GPUs. Let's look at overall linear solver speedup in 6 cases, covering a variety of applications. This is a solo car steady-state RAM simulation with 3.8 million nodes. We can see GPU can offer 3 times of speedup. This is a steady-state thermal simulation of electric gearbox. I need to point out that the flow field was computed by Altair's NFX, a particle-based CFD solver on GPUs. The AcuSolve solves the thermal field. The linear solver here is GCLDR, and we can see GPU can offer 5 times speed up. This is a steady state propeller case using multiple reference frame. And this is a breaker cooling case with steady state flow and thermal simulations. Here is a steady state flow and thermal simulation of electronic heat sink. This is a transient RAN simulation of cabin comfort problem with flow, SA model, and the thermal equations. So regarding the GPU over CPU speed up, I need to point out that the CPUs and the workstation used for the slides is already top of the line, and the thread binding policy used is the one which can maximize utilization of the memory resources. So the CPU timing, though cannot compete with GPUs, is already very good. So the GPU-CPU comparison here is fair and solid. On a less powerful machine, we will see more speed up from AMD GPUs. So based on the timing information from those benchmark cases, we can see that on workstations, for memory-bound programs such as large-scale linear solvers, adding more CPU cores after a certain level cannot speed up the program. Instead, the GPUs are better suited for this kind of application because of the larger memory bandwidth. And AMD Radeon Pro 7 can deliver 3 to 5 times of speed up, comparing to 32 CPU cores. At the end, I will briefly talk about the source code porting procedure. I can be brief because the procedure is quite straightforward. Thanks to the HIP RockM APIs, the RockM library currently used for AcuSolve is version 3.8. In fact, the RockM 3.9 has been released not long ago. The Hipified Perl tool is quite useful to convert existing CUDA code to the HIP syntax. Then the HIPCC, HIPCC compiler can compile the kernel code for AMD GPUs. Because HIPCC requires LLVM support, I suggest the developers use the Docker image provided by AMD, which includes all the necessary components and an environment to build the HIP code, HIP kernel code easily. This AMD GPU target flag is used to produce a machine code across different generations of architectures, so that the same application executable can directly run on older and newer AMD GPUs. As for regular C++ files, which only make function calls of the HIP RockM APIs, the compilation is easy. We just need to give the include the path and use a macro to tell the specific platform we target is HCC for AMD. If we are using Intel compilers to build the C++ files, I found that the minimum version required is ICC 2019. And for the header to be included, the first HIP runtime is necessary. We can also include the header for profiling, and specific for sparse linear algebra problems. We need to have RockBlast, RockSparse, and RockSolver, which includes functions such as CSR, BSR, SPMV, and QR decomposition. Right. During the linking, we need to explicitly list the HIP runtime library and all the RockM math libraries. And for the application program delivered to the customers, we need to ship all those ship those 7 libraries, shared libraries with our program. So at the end of this presentation, let me summarize. AcuSolve is a powerful general purpose CFD software that is suited for large-scale industrial applications. Recently, we have ported the linear solvers in AcuSolve, usually the most time-consuming part, to GPUs. And we have seen impressive speed up, especially on AMD Radeon Pro 7, we see 3 to 5 times speed up. And the source code porting procedure using the HIP RockM APIs is straightforward. So we encourage more people to start exploring and implementing with HIP RockM to leverage the computational power of the AMD cards for their HPC program. Thank you very much. If you have any questions, please send me an email. I would be happy to answer.